Welcome back. Ah, nice, huh? I thought I'd Andersonify my videos a little bit. So it might look a little wavy, but I promise in person it looks really straight. It looked perfectly straight when I put them up there. So hopefully, it makes things a little more colorful around here. Hopefully it's not too distracting because I like it and I'm keeping it no matter what. So we were in chapter 5 and we discussed this formula for calculating z-scores. And if I were to get a tattoo, I don't have any. If I were to get a tattoo, I've got two main contenders. One of them is the z-score formula, and the other we'll talk about in just a few minutes. I also get the opportunity, if any of you know Mr. Z, if you have pre-calc or calculus with him, whenever I find myself in his room, without his knowledge, I write this somewhere in his room, whether it's on a table, a board, something. I've graffitied almost every surface in that room. So if you've ever seen that in there, that was me. Or maybe someone in one of my classes that I told that to. But yeah, I'm trying to invade his life with statistics. So anyway, we were talking about this formula. And we use this in order to take an observation from a distribution and standardize it. So we say that a distribution has this mean and this standard deviation. So if we take an individual from that population, subtract its mean, divided by the standard deviation of the population, we get that z-score, which is a measure of how many standard deviations above or below the mean that individual is. So let's talk a little bit more about this. For what shapes of distributions do we use the mean as a measure of center and the standard deviation as a measure of spread? Symmetric without outliers, right? It's for those really nice distributions, symmetric without outliers. So think of a histogram for a data set that has those properties. Symmetric, no outliers. And let's say that we keep adding data. We keep adding it and adding it and adding it. So if there aren't too many values in the data set, that histogram is going to look really choppy. Like it might have a really tall bar in the middle and like not very tall bars and then smaller bars and then smaller bars and then smaller bars. Imagine we keep adding data so that histogram smooths out. So you have a tall bar here, and then smaller bars, 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 very small bars toward the edges. If we keep adding data forever, if we have an infinite amount of data, that histogram might end up looking something like this. I'm so excited. Is that a good one? Does it look better from a distance? That's actually pretty good. Yeah. Looks like this, right? So this isn't really a histogram because instead of a bunch of bars, I've drawn a curve. But that's because it gets more and more curvy the more data you add. And we'll see that again later in the year, maybe toward the end of the fall semester, early spring. But this is what a unimodal, symmetric, without outliers data set would look like if you had a lot of data values. And data sets that have this shape are very common. They're everywhere. It's a very common shape. So like, I've got a whole list of things here. Body temperature for humans tends to be distributed this way. In the middle, we've got, you may know, 98.6 degrees Fahrenheit. Some people's normal body temperature, they run hot. Some people are a little colder on average. But most people are near that middle 98.6 value, which is why that's the rule of thumb. The weights of, and I purposefully left this empty, it could be any number of things. Weights of people, you'd actually have to restrict it by gender, because the weights for males would look something like this, and weights for females would look something like this. But if you put males and females together, it does not look like this. It would actually be bimodal. You would have a hump for females and a hump for males as well. So weights of, I've got loaves of bread, for instance. So let's say you use the same ingredients in a bakery to make a loaf of bread. There's gonna be variability a little bit in there, but the average bread loaf is gonna weigh some amount. You're gonna have some that are heavier and some that are lighter, but most of them are gonna be in the middle, and the variability is gonna be symmetric in shape. Let's see here. Standardized test scores usually follow this shape. Again, most people, the most common score, right smack dab in the middle. Some people do really well, some people do really poorly. Battery life. Maybe you've got the newest iPhone, but you find that your battery is dead after 3 hours if you are doing something intensive. Okay? Some people's iPhones are going to have longer batteries, some are going to be shorter. Just because they're made of the same materials does not mean that all phones have exactly the same battery life. The distribution is truly something like this. Okay? I could be here for the rest of my life listing all of the variables that have a shape like this. It is very common for variables to have this shape. And there are other variables that have different shapes, but this is the most normal shape. This is the most normal shape. This shape has a name. It's the normal distribution. It's so normal, that's what it's called. It's amazing. And it's because so many variables naturally have this type of shape to their distribution. So, it turns out a chunk, okay, more than a chunk, most of this course is going to be about this and what we can do with it. In the one semester class, if you took it, we called statistics I forget exactly what the phrasing was, but we collect, organize, analyze, and interpret numerical information from data. We're going to be doing all of those things primarily with this distribution because it's so common, because it's so normal. We are going to talk about other things. For instance, this is only for continuous quantitative data, right? If we've got categorical data on this axis, it's not going to work. These have to be numbers. But for pretty much any quantitative data that's continuous in nature, like these or any others, most of them have this shape. I think I'm confident in saying that. So let's say a few things about what we notice about the shape here. So the normal distribution. This is what we call a bell-shaped curve. It's not perfect, but if you think of like the Liberty Bell, if you've seen a picture of it, it's that general shape, and that's the generally accepted term for what this looks like. It is unimodal and symmetric. And it is a model for a population. It is very important that you understand the distinction here. When we are talking about this curve, we are not referencing a sample. this is a population. This represents a population. Okay, and it's what we are estimating that it looks like. Okay, a sample will never look like this because a sample would give us a histogram with bars. Since this is a nice, neat curve, it's what we aspire to. It's what we're basing all the things we're going to talk about on. But this is never, ever a sample. A sample cannot have a normal distribution. That is impossible. Now, a sample can have a normal-like shape, but it will never be a curve. It will always be a jagged histogram that has edges, right? So this is a model for a population. This is the ideal. This is not anything that's actually attainable, right? And what we talked about here with z-scores, this is going to become very important for how we describe the normal distribution. And this is just another case where when we talk about population, mu is the population mean, sigma is the population standard deviation. So when we're calculating z-scores, generally we're talking about a population, right? How does this individual relate to the population, mean and standard deviation? Right. So let's see here. We're doing good. We're a decent way through the notes here. It has many properties. Oh, right. So this distribution is amazing, not only because it represents the population of so many different variables, but because there are so many ways we can analyze a data set if we think that it comes from a population with this shape. There are so many tools that we're going to have in our toolbox that we can only use if we think the population has this shape. So let's see here. Okay. So if we were to have a data set and create a histogram from it, and the histogram looks roughly bell-shaped, unimodal, and symmetric like this, but as a histogram, then we can apply a whole bunch of different statistical procedures, starting with this one. So I'm going to draw another curve here. I'm not going to draw it in black. That would be a mistake. Okay, so I've drawn what is quite possibly the largest normal curve I've ever drawn in my life. But we're going to talk a little bit more in detail about how we can break this up. So let's suppose we have a variable whose population we think looks like this because we got a sample and the histogram looks bell-shaped, unimodal, and symmetric. We can say the value directly in the middle, that's about what it looks like, right? Let's assume this is directly in the middle. This is not to scale necessarily. Okay, right in the middle, that's the mean. Right? That is a feature of this normal curve, is that the mean is the value directly in the middle. Okay. Now, a variable that has a normal distribution we say this is shorthand, right? We say that the variable x, whatever x is, whether it's body temperature, battery life, whatever the variable is, follows a normal distribution with a mean of mu, whatever that number is, and a standard deviation of whatever sigma is. Okay. As we look at examples in a little bit, we will see what this looks like for a real variable. But in general, this is how we define the model, right? It's a normal distribution with a mean mu, standard deviation sigma. These two values determine what this looks like. For different values of the mean, this variable might have a mean here, another variable might have a mean here. So everything's just shifted over. If we change the standard deviation, we can squish this to be closer together or flatten it out so that it becomes really wide. And so just by changing these two numbers, we can make this curve look, it'll have the same basic shape, but it could either be flatter or narrower or shifted anywhere along the line. So the mean will always be in the middle though, because it's the mean, and since this is a symmetric curve, that mean is in the middle. Now, we've already decided when we calculated z-scores that the idea of using the standard deviation as kind of like a ruler, saying that a particular value is so many standard deviations above or below the mean, is an important thing to do. So let's continue with that idea and count along this axis standard deviations above or below the mean. So if the mean is in the middle and we go this way, we're going to the right, so the number's getting bigger. I hope I'm not being patronizing, right? We can say that whatever this value is, it's the mean plus a standard deviation. We can go further. This is the mean plus one standard deviation. If we add another standard deviation, that's the mean plus two standard deviations. This would be the mean plus three standard deviations. Okay. And we already know that for a symmetric distribution without outliers, anything more than two standard deviations away from the mean is an outlier. So that's anything bigger than this number. Notice most of the curve is in the middle. Anything out here would be considered an outlier for a particular data set. So we can count by the standard deviation going to the right. Let's do the same thing going left. Instead of adding standard deviations, we can subtract. That's the mean minus one standard deviation, mean minus two standard deviations, and the mean minus three standard deviations. Okay. We don't need to go too much further. As we'll see in a minute when we finish this up, there's not much to the outside of three standard deviations to each side. This is almost the entire curve. The curve does go on forever in both directions. It is continuous, but there's so little area out to the ends, we typically don't even care about them very much. Those of you in calculus getting vibes of antiderivatives, maybe you're there, maybe you're not. We will be doing something similar to that, but we won't be using calculus for it. We will be calculating areas under this curve between values, or to the right or left of the value, but we're not going to be doing it by hand. You could, and if you go to graduate school in stats, you will, but the function of this curve is real nasty, and we're not going to deal with it. So, we can count by standard deviations above and below. And there's something really neat about this shape in particular, this normal curve. As long as you know what the mean and the standard deviation are for a population, you can figure out what these values are pretty easily. But the cool part comes when we start seeing how this curve is portioned. So, actually I want to use different colors here and not knock my mic over. Okay, so let's say that we make a line straight down to mean minus one standard deviation and do the same thing at the mean plus one standard deviation. Okay, I've effectively portioned this curve into three pieces. This is a piece, this is a piece, and this is a piece. What we're interested in here is how much of the curve's area is in the middle, in between these two values. What percentage of a population has a value within 1 standard deviation of the mean. Now, the whole area under this entire curve is equal to 1. So we're going to be talking about how much of that curve is in each of these areas as a percentage. And it turns out, inside this middle area, within 1 standard deviation, is 68%. More than 2/3 of all data values, if the population has this shape, more than 2/3 of the data values are within 1 standard deviation of the mean. 68%, approximately. Okay, these are all approximate, not exact. Right? So truly, most of the curve is right here in the middle. So this curve is not really to scale, but you get the idea. Okay, but we know more than just that. What if we go 2 standard deviations out? Okay. Oh, by the way, if we say that 68% is in this middle area, you could figure out how much is in each of the ends, right? If 68% is in the middle, how much is left over for both of these? It'd be 100 minus 68, 32% total between these two. So how much is in each one? It is 16 in each side because this curve is symmetric about the mean. So 68% in the middle, 16% on each of the sides. That also means if we were to split it right down the middle here as well, each of these two pieces would be 34% of the data. Yes, 34% of the data is in each of these two halves of this middle section. Okay. But let us further subdivide here and make lines 2 standard deviations out. Now, we're involving more of the curve. So how much of the data is within 2 standard deviations of the mean on each side? It's going to be more than 68%, obviously. That number is 95%. 95% of data values, approximately, for a population of this shape, 95% of the data values of the population are within 2 standard deviations of the mean. So when we say an outlier is at least 2 standard deviations out, outliers are only out here, in that outside 5%. Okay? In each of these ends is only 2.5%. So for a data value to be considered an outlier, it would have to be in the outer 2.5%, either on the low end or the high end. There's still one left, right? Let's go even further. 3 standard deviations on each side. Three standard deviations on each side, we're going out even further, an even bigger percentage. (99.7%) approximately of data values from a population of this shape are within 3 standard deviations of the mean. Virtually all the data is within 3 standard deviations of the mean on either side. Now you see why we don't go much further. It would be kind of pointless. If we went out to 4 standard deviations, that number would be even bigger, but there's really not much of anywhere to go from here. This is practically 100%. The only values more than 3 standard deviations from the mean on either side are your serious outliers. Very, very serious outliers. So, if we know from looking at a histogram from a data set that it has this shape, again, it's not going to be a curve, it's going to be a histogram, it's going to have bars. But if we think that we can attribute this shape to the population, we can say this about the data set. We can say that approximately 68% of values are within 1 standard deviation of the mean. 95% of values approximately are within 2 standard deviations of the mean. And 99.7% approximately of data values are within 3 standard deviations of the mean. That's really powerful that we can say that. It gives us a lot of context of what is strange, what is normal. Normal. But this set of properties has a name. It actually has 2 names. I kid you not, one of its names is the 68, 95, 99.7% rule. Just so you remember the numbers. They are pretty important. They do come up occasionally as we go through the course. That is one of the names. And if you remember that name, you'll remember the numbers. It is also probably more widely in professional circles. It's called the empirical rule. And the reason it's called that is because this is not a mathematical law. This is statistics. This is the study of uncertainty in data. This was figured out empirically by looking at populations of these variables. They noticed that if they had this shape, they noticed that based on the standard deviations, they saw approximately these numbers over and over and over and over for so many different variables. It came about empirically through data. So that's something we can know about a data set if we think it has this shape as the population. So that's pretty dope. Am I allowed to say that? I hope so. It's dope. I love this. The normal distribution is so cool. But we can only use this rule for something that we think has a normal distribution from its population. So the empirical rule, just to make it very clear, states the following. I'll just edit me writing it out. It'll just appear here. So there you go. This is what the empirical rule, or the 68, 95, 99.7% rule states. Approximately that percent of data values are within however many standard deviations of the mean. And again, that only applies for populations that have a normal distribution. Fantastic. So, let's see it in action. An example. Now, let's talk about babies. Babies. Baby birth weights. And this is pretty well known. That the birth weights of babies do have a distribution of this shape. It's normally distributed. It has a normal shape, right? Once babies grow up, females and males tend to weigh different amounts on average. But at the beginning, that distribution only has one peak. It's unimodal, it's symmetric. Okay. And we also know the mean and standard deviation with an average of, take a guess, how much does the average baby weigh when it is born? £7.6, or pretty close to it. And a standard deviation of 1.3 pounds. Now, that's just a statement. That's not a question yet. But based on this, we can draw this. Now, let's see here. Yes. I really, really do want you to draw this curve again in your notes. Draw it again. Don't use this one. Practice makes perfect, right? Draw this curve again, but you'll be able to actually label the values on this axis because you know what the mean and standard deviation are. we can tell from the information here that X, which is the birth weight of the babies, follows a normal distribution with a mean of 7.6 and a standard deviation of 1.3. So when you draw this model using the values for the mean and the standard deviation, you should be able to come up with the values on that axis. I would like you to draw that model. Go ahead, pause the video, come back when you've got it. Okay, so your model should look like this, right? And that includes the 68, 95, and 99.7% lines as well. And you can see the numbers that I've got across my axis. Yours should match those. In the middle, we've got the mean, which is 7.6. And then if we're adding one standard deviation at a time, we're adding 1.3 each time. If you wrote this as 7.6 plus 1.3, yes, that is 8.9. You might want to write that as 8.9 instead. Okay? And then we're subtracting 1.3 each standard deviation we go that way. So, I've got a few questions here that we should be able to answer by using the model that we've drawn here. And I hope that what I'm instilling in you is, if you are ever told that something follows a normal distribution and you have the mean and standard deviation, drawing this is step one. Okay? At this point in time, drawing it with the 68.99 or 68.95, 99.7 is included. In the future, you won't need these values, and I'll tell you why in the next video. But for now, in this chapter right now, you should be drawing this with that included. Especially if it says draw and label the model. Definitely do all that. So, let's talk about these questions. Okay? What percent of babies weigh less than 5 pounds? That's our first question here. Sorry, I had to write it a little small so everything fit. What percent of babies weigh less than 5 pounds? We can answer that using our model here. 5 pounds is right here. So what percent of babies weigh less than 5 pounds? The percentage of babies that weigh less than 5 pounds is the same as the area under the curve to the left of 5. It's this area right here. Okay? We need to find what this area right here is. What percentage of the curve is there? And that's where these numbers come in. Now, the answer is not any of these numbers, obviously, but we should be able to use what we know to help us figure out what that area is. Maybe you've got an idea? Let's try and figure it out. Okay? So, 5 pounds. 5 pounds right here. That's 2 standard deviations below the mean. So that is at the end of this area. 95% is in here. But we want to know this area here. So if this area is 95, that means 5% total is on the ends. And since this is a symmetric curve, that means each of these areas is 2.5%. So this area here that involves all of this, all the way up to like here, all the way to the end, is 2.5%. So that's our answer for that one. 2.5% of babies weigh less than 5 pounds. Some people find that hard to digest the first time around. It might take a few of these for you to get more used to how to manipulate these values to get any possible area under the curve. So let's do another one. These are ditto marks. I was shocked. I've used these in the past and people were like, what the heck is that? This just means I want to write these words again, but I'm lazy. And I don't want to. So this is asking what percent of babies weigh less than 10.2 pounds. Okay, so instead of taking the area from here down, we now want all the area from here down. Well, there are actually a couple ways of doing this. One way would be to figure out what this entire area is. You could also attack it as, you could take the area of the entire curve, which is 1, and subtract the part that we don't want. You could do it that way too. So either way is fine. If you want to go ahead and tackle that, go for it. But for this particular problem, especially since we already know what this area is, I think it should be easy to calculate what all this area is. 10.2 is 2 standard deviations above the mean, so it goes up to here. And this area is 95%. And we just found out the rest of the area to the side is 2.5%. So everything less than 10.2, if we add those up, would be 97.5%. If you've got this, if you feel really confident with problems like this, awesome, great. If it's still kind of a stretch, maybe if you still don't get it after all these questions, that might be time to come to virtual office hours from 10 to 11 a.m. on Mondays and 1 to 2 p.m. on Wednesdays. I'm on Zoom. You can ask me, hey, Mr. Seplick, remember when you were calculating those percentages from the normal curve? I didn't get that at all. We can do some more examples. I can try to explain it in a different way that I can't fit in on this video because I'm going really long. So we're going to go ahead and keep going here. But if you've got questions, you can get them answered. Or you can just email me and we can set up a Zoom whenever you want. What percent of babies weigh more than 6.3 pounds? So now, more than we want from here up. So here starts the 68%. So from here to here is 68%. We would also need everything from here up. Or we could just figure out what the area is from here to the left and take 1 minus that. I like doing it that way. Let's figure out what this area is, everything to the left, and then take 1 minus that. So this is 68%. So when we first said when we had this curve, we said these areas combined are 32%, which means each of these is 16%. So that means this, all of this is 16%. So everything more than 6.3 would be 1 minus that. That would be 84%. Oh, let me do that in a different way. 84%. And just really quickly at the end here, I do want to talk about a couple other, well, not a couple other, one other type of problem. These are taking a value on the axis and having you respond with a percentage. But we could go backwards. 2.5% of babies weigh more than what amount? 2.5% of babies weigh more than what amount? So we're looking for where 2.5% is. We already know that's this end, and it's also this end. It's everything more than 2 standard deviations away. So this is also 2.5%. So 2.5% of babies weigh more than what amount? We want to know where is the value at which only 2.5% of the curve is higher than that. This. That's from here up. So that's 10.2 pounds. And the last one I'll leave to you. If you feel like you can do it, pause the video. 0.15% of babies weigh less than what amount? 0.15%. That's such a small percentage because it's half of 0.3%. Right? If 99.7% goes all the way out here, then these two ends combined are 0.3%, which means each half is 0.15%. So that percentage of babies weigh less than what amount? That means we want the 0.15% to the left of that number, 3.7 pounds. All right, so I apologize, this video was a little longer than I thought it would be, but you learned so much stuff. We introduced the normal distribution, right? Super, super common, really useful for this course. We learned how to write it. We learned what kind of variables have a normal distribution, how you spot it. We learned about the empirical rule and what it says. And we did a whole bunch of different problems using the normal distribution and the empirical rule that let us determine how much of this curve is at different points. So that's enough for this video. In the next video, little spoiler, what if we ask about numbers that aren't on this line, at least that we don't have tick marks for? What percent of babies weigh more than 9.6 pounds? Can't use the empirical rule to figure that out. You've gotta have another way. So we're gonna figure out how to do that in the next video. If you haven't looked at the Unit 1 progress check on AP Classroom, make sure you look at that. It is super important that you do not wait until the last minute to do that. You will hate me and maybe yourself if you don't start soon. And the next video will be the last one in Chapter 5. So the Chapter 5 homework is also on Canvas. You could probably tackle a good chunk of that homework assignment before tomorrow's video. So you can go ahead and take a look at that as well. So for now, have a great day, and we'll see you next time.